Okay, probably we are ready to start. It is my great pleasure to introduce my friend Serhii Gryshchuk. Serhii, I apologize. Probably full spelling of your talk should cut a couple
Yes,
of
yes, yes.
monogenic function with values in commutative complex algebras of the second rank with unity and generalized biharmonic equation with non-zero simple characteristics. Please.
Thank you very much, Anatoly. Nice to meet you all participants. To hear, not to see, but to hear. It's a great pleasure. So you can see this presentation is done by the spirit of Yuri Strachimchuk. It's handmade style, as you can see. So consider the generalized biharmonic equation 1. This is a fourth order equation with constant complex coefficients. You can see that this equation is a generalization of the biharmonic equation. We assume that the B5 is not equal to 0, and the characteristic equation of the equation 1, the equation 2, has pairwise difference roots. We denote it by the ker L, the star formula. So each root is k is a simple root, and all of them are different. A particular corollary from this is that also not the B5 is not equal to 0, but B1 also isn't equal to 0. By the equation by the solution of the equation 1, we mean, as usual, some function defined on the domain D of the Cartesian plane x or y, having continuous derivatives up to the great order 4. Denoted by B star, a commutative associative Banach algebra with the rank, with the second rank, having a unity. We denote a unity by E. Denote by E1 and E2, a basis of the algebra of B star, satisfying the equation 3. As you can see, the equation 3 is a hypercompass generalization of the biharmonic of the characteristic equation 2. Our first problem is to find a path of B star and each basis E1, E2, which satisfies this condition 3. Possible candidates on algebra B star is 2 of them, because we know that up to isomorphism there is 2 such algebras. This is algebra B, generated by the unity and the nilpotent row, and algebra semi-simple algebra B0, generated by the unity E and idempotent W. It's evident that algebra B0 has a basis composed by orthogonal idempotents E1, E2, and there is such relations between this algebra, this basis, and basis E and W. And this is basis is very convenient. So we find a basis element which you need in decomposition of this orthogonal basis. So we have theorem 1, which gives an answer to our question. It says that the algebra B doesn't contain any basis E1, E2 satisfying condition 3, and all bases of B0 satisfying condition 3 are represented in the form 6. Here, alpha and beta are different complex number, non-zero number, and C1 tilde and C2 tilde are different elements from the roots 0 star. This is roots of the characteristic equation 2, different. And we have a simple corollary that a multiplication table of the bases 6 has the form 6, 8, and 9. Now we are ready to introduce a notion of two-dimensional plane in order to develop a technique of monogenic functions. Let mu E1, E2 is a real span generated by finding bases E2 and E3 over the real space. And let d zeta be a domain in this plane mu E1, E2 congruent to the domain D. We say that a basis E1, E2 satisfies the condition M and B if for any non-zero element from this plane mu E1, E2 except of 0, there exists an inverse element. And it's simple to prove that a basis E1, E2 of B0 satisfies condition 3 and condition NB together if and only if elements S tilde K has non-zero imaginary parts. So the condition 10 is true. Thus, we need to have these assumptions. So now we assume that our equation 1, so the characteristic equation, has roots of characteristic parts such that at least two of them are different and has non-zero imaginary parts. Now we are ready to develop a notion of monogenic functions. Any functions defined on the domain d zeta and taking values as the algebra b0 has the form 11. So there is this expansion of the function f with respect to basis e1, i1, e2, and i2. This is imaginary complex unity. And this is components uk. We denote it by an operator uk of f. This is real components. This first real component, second, third, and the fourth. This is due to the fact that each of this complex algebra is isomorphic to some fourth order real algebra. And we call a function f monogenic in the domain d zeta if at any point zeta from d zeta such limit exists. So we can see that this limit is a usual derivative in the sense of Gryshchuk, and this is a particular case of the differentiable by Gateau functions. About them, Professor Plaxer told above. But when we consider this particular case, it helps us to find more different, more application to partial differential equations due to we restrict our attention to some particular case and not to consider totally of differential by Gateau functions. So we can see that it's help us. Now we can also prove and some analog of Cauchy-Riemann condition. So the function f is monogenic in the zeta if only if its real components k are differentiables in the domain D in the real sense, and the following analog of the Cauchy-Riemann condition holds. This is condition 13. A and B are for four real matrices depending on S1 with tilde and S2 with tilde from the formula 6 with depend, which describe all required our bases. It's important for us to restrict our attention on some particular monogenic functions. This is a function which is monogenic in the domain D zeta and have derivatives which order more than 4. And we have such lemma. The function f belongs to this class if and only if each component, real component of such function, is a solution of generalized biharmonic equation 1, and the quadruple of this function satisfies equation 13. This is a general statement. In some particular cases, it's also proved. No, I'm sorry. This is about another situation. So let zk is a complex variables which built by use of x and y elements from the coordinates of the point x and y of the domain D, and ck with tilde. This is such elements which is considered in the formula 6. Theorem 3 gives a representation of monogenic functions. Function f is monogenic in the domain D zeta if and only if it has a representation 14, where f1 and f2 is an analytic function of its real if its complex variables defined on the such domains D zk. A very important case is a case of conjugated complex characteristics. If, except of exception 10, we have an extra one, that conjugation of the S2 with tilde isn't equal to S1 with tilde. So we have conditions 15. So this and imaginary part doesn't equal to 0. Also, if we assume that all coefficients are real, and D is a bounded and simply connected domain, then it's well-known fact, which is proved for some cases, deals with anisotropy plane theory by Leknitsky, and it also can be proved by this similar method that general solution has such representation 16. Here, f1 and f2 are complex functions. Having the previous theorem, we can see that this representation can be rewritten in the form 16. Here, f with u is a monogenic functions having such form. Here, f1, f2, f2 coincide. And using this fact, we can prove theorem 4. This is a natural analog of the representation of harmonic functions by use as real component of analytic functions of complex variable. So let U is a fixed solution of equation 1. Coefficients bk are real. D is a bounded and simply connected domain. Then all monogenic functions from d zeta to b0, such that the first real component of them, U1, I, this one. Coincide with this fixed solution can be expressed in the following form 16. And if in general case we can't find this, so here fu we have in explicit form. This is such formula. But in general case, it's a great problem to find a total of such functions monogenic f0. So in general, we can say that this is solution of 13 of such form. But also it's possible to find all this totally of f0 functions in explicit form if we restrict our attention for some particular cases of such equations. Well, this is done. And also it's also considered by me applications of this equation 1, where it is an equation of finding the stress functions for anisotropy plane theory. First, it find by some particular case when the equation 1 is a solution of finding the stress function for orthotropy plane theory, and then it is find how to find the solution where this equation is equation of stress on finding the stress function for general case of plane anisotropy. Thank you very much for your attention.